So this is the last lecture of the 3030 Advanced CMOS Technology and the Industry Trend. This is not part of your final exam, but I think this will help you to understand what's going on in the industry. We will post all the marked version into the canvas after today's class, this evening. All right, so we have talked about the CMOS scaling in the 3030, and you have seen the Moore's law, and also we talk about the Daniell scaling, and you have the constant field or constant voltage scaling, and this is the trend of the scaling, and all have this technology nodes like 65, 45, 32, 22, 16, 11, and I think industry named this as 7. And this is a trend, but we see a slowdown in the recent years. And actually, for the physical dimension of the gate length, it deviates from the projection. So here the projection is a solid line, but the actual gate length, the dash line, actually deviates from the projection. It's not that small. This is because of the challenges in the scaling we will talk about in the next. It's very hard to make the transistor short. The channel has to be maintained for a certain distance from the source to the drain. But today, the industry is at 7 nanometer, like TSMC and Samsung doing the volume production at 7 nanometer. And also I read the news, TSMC is going to have the 5 nanometer process available this year. So we will say 5 nanometer this year and probably 3 nanometer in 2 or 3 years. So the scaling is still going on, but it's becoming more and more challenging. To maintain this kind of scaling trend, the industry actually introduced a few key technology in the past few generations. And we will discuss that shortly in this lecture. So one of the innovation is this high-k metal gate introduced by Intel at 45 nanometer technology node. This is to replace the gate oxide from the silicon dioxide to some higher K dielectric, for example, hafnium oxide. And then at 22 nanometer, Intel also introduce the FinFET structure. This is to change the transistor from what we discussed in this class, the planar MOSFET structure, to a 3-dimensional FinFET structure. And we will talk about that in a minute. And the industry is discussing the possibility to have this so-called stacked nanowire in like 3 nanometer node. This is still under research. It's not finalized yet. But this is going to happen probably in the next couple of years. So let's look at those trends in the next few slides. And you have seen this IDVG and IDVD curve in this class. I will skip this. And we also talk about the subthreshold slope in the class. And we care about this subthreshold current because that will determine the off-state current, which will determine the standby leakage or leakage power of your chip. And this is the structure of the conventional bulk MOSFET we have discussed so far. So in this class, we talk about the MOSFET, which is based on this conventional bulk MOSFET. We call it bulk because here is a silicon substrate. It's like a bulk. And this is the top view layout of the transistor. We have the W and we have the L. Okay, so what's the problem of getting shorter channel? If your L of the gate become too short, then there's problem of the drain effect on the source barrier. And actually we discussed briefly before in the lecture, maybe lecture 7, 8 or 9. So the problem is the drain current, the drain voltage will affect the drain current. which is not ideal. Ideally, you want the gate voltage control the drain current. For example, here you see those, for example, this non-channel transistor. This is the energy band diagram from the source to the drain. And you know this is the source, this is a gate, this is a drain. So the current flow ideally should be controlled by the gate. If you apply gate voltage, you know you are going to push down the band, which will affect the barrier here, and the electrons can jump over. So you can have the conduction. Ideally, the drain voltage will not affect this barrier. For example, in this non-channel device, non-channel means maybe hundreds nanometer or 1 micrometer down the L. If you have a non-channel device, then when you increase the drain voltage, you push down the band of the drain side, but it will not affect the source side because they are too far away. Okay. So if you have this non-channel device, then if you look at the IDVGS curve, when you have different drain voltage, then they will not change. You only have one green line here. So this is a good device. But what happens if you reduce the L to be the short channel? For today's like 10 nanometer, for example. So if this channel is too short here, when you increase the drain voltage, you push down the band because it's so close to the source. So this barrier will also reduce. That means you are going to have more electrons jump over the barrier, more current, even though your gate voltage remains zero. Your drain voltage can open the channel. So if you look at the IDVG curve in this subthreshold region, you will see the increase of current will increase the drain voltage. You see these two red curve. So as you increase the drain voltage, the off current will increase. So that means the drain will control the current instead of the gate control the current. So this is not good. Ideally, the transistor is a gate control. So this is the problem of this short channel effect. And why do we care about the on-state current and off-state current in the transistor? So here is the data from Intel. 45 nanometer and 32 nanometer, 2 generations. If you keep the same on current here and look at the off current, it will reduce by 5x off current. Or if you keep the same off current here, then the on current will increase by 14%. So this is the benefits of the scaling because we want large I on, small I off. From the circuit performance we discussed, for example, in the inverter or in general for digital circuit, the delay is given by C VDD divided by I on. If you have large I on, you have smaller delay. And also for the power, one of the power component is the standby leakage power, which is I off times VDD. And then if you reduce I off, then you reduce standby leakage. So by the scaling, you wish that you can push this trend towards this corner, which means larger I on, smaller I off. And this is motivation to do the scaling. And when you do the scaling, you may achieve that. And then the industry realized the challenge in the short channel. As we discussed, the drain will affect the source. So how to overcome this challenge? And the technique here is called the 3D FinFET technology. So here we compare the traditional planar structure versus the 3D FinFET structure. In the planar structure, so here we have the source and the drains on the other side, and we have the gate. So the gate is covering the surface of the silicon surface, and the current is flowing, or let's say electron is flowing along the surface between the interface of the gate oxide and the silicon. So it's a planar two-dimensional current. But the problem is when the drain is so close to the source, this gate cannot control. Okay. To increase the gate control, here's the idea is to build this three-dimensional structure, and we call it a fin. So it's a very thin wall. It's like a fin of the fish. And the gate now is surrounding the two sides of the wall, or two sides of the fin. So the gate can wrap around the fin. So the gate has better control of the channel, because it can have both sides to control the channel. And in the planar structure, it can only have the top surface, only one side control of the channel. But in the 3D-dimensional FinFET structure, the gate can have the control over the channel better. So you can be more gate control. That means the drain effect will be less. I don't know if you can see my camera here or not. If you think about the three-dimensional fins, like my smartphone here, this is the fin, and the gate is surrounding the fin like this, both sides. So the current will conduct in this fin along the surface here. So this is the FinFET concept, and the FinFET was actually proposed in 1998, like 22 years ago, from a university group from UC Berkeley, and the inventor was Professor Chae-Min Hu. And if you recall, he is the author of our textbook on the semiconductor devices. You use that for the first half of the semester. He is the professor who invented the FinFET technology. And his group published the first paper in this conference called IEDM, International Electron Device Meeting, in 1998. This is the original design, the layout of the FinFET. And then this is the IDVG and IDVD curve of the transistor built in the university lab. And at that time, those are the dimensions for the fin structure, because the fin is a three-dimensional structure. We need to have those numbers. So in this case, the width of the fin, which is this W fin, is 20 nanometer, and the height of the fin is 50 nanometer, and then still this is the gate length is 30 nanometer. So this is the FinFET, first FinFET in the world. And after this paper, there are many research going on in the universities and also industry. But after the efforts of, let's say, 14 years, in 2012, Intel first commercialized the FinFET in production at a 22 nanometer load. And here is the microscopic image of the Intel's FinFET at 22 nanometer. And here, this is the bird's eye view of the FinFET. So here, this is the fin, and then the gate is surrounding the fin like this. And this is source and drain. This is source and drain. And if you cut the chip along the gate direction, if you cut that, this is the cut gate cross-sectional image. So if you cut along this gate direction, you will see this kind of image. The fin will be in and out of the plane. And you see the fin is very thin, like only 8 nanometer in the fin width, and height is 34 nanometer. And if you cut the fin direction from the source to the drain, if you cut, so this will be the cut fin image. So this is source and drain contact, and L is here, around 22 nanometer. So this is the let's say structure of this FinFET. And I just want to mention one difference between the FinFET and the conventional planar MOSFET is that the W in the FinFET, now the current is flowing along this sidewall. So the effectively the W is this, because the current will flow along this interface between the fin and the oxide surrounding that, the gate surrounding that. So the effective W per fin will be given by 2 times the height, roughly the height of the fin, plus the width of the fin. So this is the height of the fin, and this is the width of the fin. So this is unlike the planar structure, where the current conduct along the surface of the silicon wafer. This one, the current is conducting in this three-dimensional configuration. Okay, so this is a FinFET, and it has become the mainstream technology from 22 nanometer, and also the 14 nanometer, 10 nanometer, 7 nanometer, and 5 nanometer. So today's chips are mostly based on this FinFET. So the technology trend, okay, we have talked about the FinFET structure, and FinFET most benefit. This is a FinFET. Most benefit is to reduce I-off. This is to reduce I-off because it has better control of the gates. The other technique we introduce is to increase the on-state current. One is this gate dielectric change from silicon dioxide to the high K, typically like hafnium oxide. And the epsilon for silicon is the dielectric constant is 4. This one is like 20. And you know COX is epsilon QX. And you also know the on-state current is proportional to this mu COX W over L. And then you have voltmeter. So you want to increase the COX to increase on current. And also you want to increase mobility, mu, to increase on current. So how to increase mobility mu? One technique is called the stress. That means you are going to squeeze your silicon to apply stress, which will increase the mobility. The other technique is to introduce other material into the channel. So today's PMOS is typically silicon germanium alloy. It's not pure silicon. So if you introduce germanium, it will increase the mobility, especially for the holes. So those are the innovations that the industry is doing to further increase the on-state current, reduce the off-state current. That is to maintain the benefits of the scaling. As you scale, you get better performance. As we discussed, on-state current, off-state current will determine most of the performance metrics, like your delay and the power. So those are the performance of your circuits. So lastly, we want to briefly talk about the industry model. So let me stop here for a while.